Hello everyone. Today we're going to learn a little bit about some periodic trends. A reminder about our periodic table and how it is set up. The modern periodic table consists of rows known as periods and columns known as groups or families. Our elements are ordered but in order of increasing atomic number. So, what is a periodic trend? A periodic trend is a pattern in a property that the elements have that repeats or is in some other way predictable. These trends can be for either physical properties like density or atomic radius, or for chemical properties such as reactivity. So, a couple of easier trends to start off with, some of which you may have already noticed if you watched our previous video about the families. The number of valence electrons for a member of the main group elements is equal to the number in the ones place for that group number. Please note this only applies to main group elements, aka those in the S and P blocks. D and F block generally do not have valence electrons as part of their discussion. A reminder, the valence electrons are the outer electrons. Another one that you may have noticed is that there is kind of a trend for common charge that is easier to show rather than describe. Again, this trend only applies to the main groups, which are the S and P blocks. The alkali metals, group 1, have a +1 charge. Their neighbors, the alkaline earth metals, are +2. Skipping the D block, we go to group 13, which are +3. Then, at group 14, it becomes plus or minus 4 as the common charge. And then they become negative and count down to 0 for the noble gases. It almost forms a peak at group 14 and then comes back down, as well as switching signs at group 14. Again, this trend is easier to show rather than to verbally describe. Another trend revolves around a property known as the atomic radius. The atomic radius is a measure of the size of an atom. It is measured from the nucleus to the outside valence electrons. The atomic radius will obviously be quite small. In fact, the size scale we're dealing with is generally on the size of 10 to the negative 10 or 10 to the negative 9 for a much larger atom, meters. The trend for atomic radius is that as you go down a family on the periodic table, the atomic radius will get larger, which makes sense. You have a lot more electrons and more energy levels being filled. You need room for all those electrons, and thus the radius must grow. As you go across a period, however, you're footing into the same energy levels, and so that won't change the atomic radius much. However, there is a trend. The atomic radius will slightly shrink as you go across a period. We'll discuss why in a little bit. Another property that we must discuss is ionization energy. Ionization energy is the energy that is required in order to remove an electron from an atom. It is sometimes expressed in a chemical equation form of some element, let's call it X, becoming its +1 cation and also kicking off an electron. This is also known specifically as the first ionization energy, energy required to remove that first electron. If an element were to try to form a +2 cation, it would then have to undergo a second ionization energy after that. As you go down a family, the first ionization energy will get smaller. As you go across a period, the first ionization energy will get larger. Electronegativity is the ability of an atom to attract electrons towards itself while it is part of a bond. Because this definition requires that elements be part of a bond in order to demonstrate this property, noble gases will not be included when we discuss this trend, as they do not form bonds. As you go down a family, the electronegativity will get smaller. As you go across a period, the electronegativity will get larger. You'll notice this is the same pattern that ionization energy had. Our fourth and final property that I wish to discuss before we discuss why these properties behave the way they are is electron affinity. Electron affinity is the energy change that occurs when an electron is added to an atom. Like ionization energy, it occasionally is represented in an equation form of some element, let's call it X, having an electron added to it in order to yield the anion. This also reveals that electron affinity is kind of the opposite of ionization energy. And this is a good thing. Electron affinity generally is a release of energy, so a negative energy change. This is convenient because that energy could be used to ionize something else. As you go down a family, the energy that is released will become smaller, aka the electron affinity is going to shrink. As you go across a period, more energy will usually be released, aka the electron affinity will grow. There is an exception to this rule, noble gases. Noble gases do not have an energy release. Instead, they require energy, just as they would have for ionization energy. So please be careful, noble gases do not follow the trend here, and so we will generally ignore them. You will notice these general trends follow the same as ionization energy and electronegativity, and are the opposite of the trend that was shown for radius. So these previous four properties have trends that are all connected to each other, specifically by the cause of them. The cause for this is Coulombic forces that are involved between the nucleus and the valence electrons. A reminder of what Coulombic force is and what Coulomb's law is. A Coulombic force is the force that occurs between charged particles. Charges that are alike, like two protons, will repel each other, whereas charges with dissimilar signs, like a proton and an electron, will be attracted to each other. Specifically, because we're dealing with the protons in the nucleus and the valence electrons, we'll be dealing with an attractive Coulombic force in this case. The force between charged particles grows if one or both of the following things occur. 1. It will grow if the charges involved increase in size. This can be that one of them or both of those charges increases. The force can also increase if the charged particles are brought closer to each other, aka the distance between them shrinks. You only need one of these two to occur in order to change the force, although you could have both occurring. Generally speaking, for what we will talk about, one of these two situations is occurring and by extension is causing each of the trends that we just observed. So let's look at an example explanation and figure out how the Coulombic force relates to our properties. So for example, why does ionization energy grow as you go across a period? So let us first consider what is going on in the atom as we move across a period. Two things we want to keep in mind, the distance and the charge. With regards to the distance, we do know that the radius shrinks as you move across a period, which could help us, but this change is actually relatively small. Another thing that is occurring here is the number of protons and also the number of electrons is growing. Those electrons are going into the same energy levels, and so that's why the radius isn't changing very much, but that change in protons is pretty significant. So let's focus on that number of protons. The number of protons in the nucleus, which we also could call the nuclear charge, is getting larger as you go across a period. This means we have an increased charge. An increased charge means there is an increased Coulombic force. This will make it much harder to take away valence electrons from an element, and therefore we would need greater energy to pull it off. So therefore, ionization energy increases as you go across a period because the larger number of protons leads to a much higher Coulombic force. Let's look at a secondary example for explanation. Let's look at electronegativity and look at how the trend behaves as you go down a family. Why does electronegativity shrink as you go down a family? Let's again look at how distance and charge are behaving to try to find the explanation. As you go down a family, we know that radius is getting larger. This is the one of these trends that is not explained by Coulomb's law. This is simply just, I need more room for electrons. The other thing that's happening is the number of protons is getting larger. Unfortunately, that won't help us with this explanation, as that would actually be more helpful to explain why electronegativity gets bigger. So as we go down a family, we're going to have to focus on this radius aspect. So as you go down a family, the atomic radius gets larger, simply because there are more electrons and they're filling more energy levels. A larger radius means the distance between the nucleus and the valence electrons, which is where the bonding is taking place, is going to be a lot larger. This means that the Coulombic force is now going to be less. So the reason that electronegativity shrinks as you go down a family is that the atomic radius is getting bigger, and this larger distance means there is a weaker Coulombic force that attracts the nucleus and the bonding electrons. These same kind of explanations can be used to explain the atomic radius, ionization energy, electronegativity, and electron affinity trends.